All right. So good morning, everyone. We are recording now. So let's continue our discussion on max flow min cut, right? Yeah, so we haven't proved the max flow min cut theorem yet. We will prove it today. And along with that, we'll also see an algorithm for both the problems, finding a maximum flow and finding a minimum cut. Okay. And I just want to state one point that I forgot yesterday. Right. So I just want to state a strengthening. Oh, I'm not sharing the screen yet. Sorry. Okay. Now can you see the screen? Okay, thanks. Sorry about that. Yeah. So before we move on, I want to state a strengthening of corollary 3.4. So, right, so the corollary is telling us when is the flow exactly equal to the capacity, is always less than equal to the capacity. And what I want to state is when are they exactly equal? So observe that. So I'll just add it to the statement. Furthermore, the flow is exactly equal to the capacity of the cut if and only if you have equality in all of these places. Does everybody agree? So you need all the x values for the for each arc in partial plus of u, you need equality, and for each arc in partial minus of u, so the edges going into u from u bar, you need the x values to be equal to 0. Okay, so that is part of the statement. And the proof is clear, because if any of them holds strictly inequality, then you will have a strict inequality over here. Yeah. Any questions or concerns regarding this strengthening? Okay, so we'll need this today, which is why I thought I should state it before moving further. All right. So our main goal today is to prove the max flow min cut theorem and see an algorithm for it, the famous Ford-Fulkerson algorithm. All right. So let's start with a more basic question. Let me draw the network that we have been looking at, the max flow instance that we have been looking at. Okay, so here are all of our arcs. All right, and the capacities that are given to us are these black numbers. Okay. I want to consider a particular flow, and I want to ask you how we can find a better flow. Okay. So let me consider one particular flow and let me put it in red color. So let's say it is as follows. It's one on these arcs, one on these two arcs, one on these two arcs, 0 on these two arcs, and 1 on these two arcs. Okay, and this is our flow x1. So the first question I want to ask, is there a simple idea to find a better flow? Okay, not a complex idea, just something as simple as you can think of. So can anybody see some way to get a better flow in this example? Or can you just state the idea you have in mind? S2V3 V4T. Okay. Okay. So what Shantini is suggesting is she's suggesting a particular directed path over here where all the arcs are utilized under capacity. And the particular path she suggested is S to V3 to V4 to T. Is that right? Okay. So that is in fact the path I want to use. So look at this path. S to V3 to V4 to T. The capacities are 4, 1, and 4, and the flows, the current X values are 1, 0, and 1. So we can increase 1 on all of those and get a better flow, right? Just to be very clear, because there are two-way arcs, I want to label these E1, E2, E3, and E4. We will find this useful later. Okay, and in particular, the arc V3, V4 here is yeah. So maybe I should have, yeah, my labels are not very good. So this is V3, this is V4, and the particular arc we are looking at is E3, which is going from V3 to V4. Okay. Later on, we may need to distinguish, so I'm just labeling them right now. Okay. So the point is that if we find if there exists an ST dipath in the given graph, in the given digraph H, right? So this is our HSTC, say Q, whose each arc is utilized under capacity. Then we can find a better flow. Okay. And in particular, let's see how much we can increase. We can increase the first arc by 3, the second arc only by 1, and the third arc by 3 again. So the best we can do is increase everything by 1. And observe that if we do that, if we add 1 to each of these X values, the conservation constraints will automatically be holding, because they were holding initially, and I'm just adding 1 at each point. So the incoming flow will increase by 1, and the outgoing flow will be increasing by 1 in this case for every intermediate node. Okay, so V3 and V4. So let's do that and let's get a better flow. All right, so I'm going to modify this and switch it to X2. And rather than making a new drawing, let me just be lazy and let's cut this 1 to 2. Let's cut this 0 to 1, and let's cut this 1 to 2. Okay, and that is our flow X2. All right. Now, at this point, I want to ask you again, can you still find, is there another ST dipath with this property in this digraph? So, is there another ST dipath with the same property? What do I mean by same property? I want each arc to be utilized under capacity. Can you all inspect the digraph and the capacities and everything and tell me if you can find such a dipath? Okay. So in fact, such a die path does not exist in this example. But turns out that does not mean that this is a maximum flow. You can actually get a better flow. So the answer to this is no. There is no such die path in this particular directed graph with these new x values. Okay. However, that being said, we can still find a better flow. Anybody has a suggestion? So I want a more sophisticated idea, right? So this was our first idea. And I'm looking for a second idea. Sorry. Okay, right. Okay, so Shantini is suggesting another path now, but is it a die path now or is it just a path? It's not a directed path, right? What you're suggesting? So I think you're on the right track. What is the path you're looking at? Right, that is correct. So let's say you're going from S to V3, is that right? Okay, so let's do that. S to V3, that is only a forward arc, so we don't have any choice. Now where are you going? V2. So that is also going in this direction. And where are you going next? V2 to V1. But this is not an under capacity arc. So what you can do is you can use the reverse arc. So the one which is going from V1 to V2, which is in the reverse direction, we will use that arc and we will reduce its flow. So let's consider this arc from, it's actually directed from V1 to V2. This is the arc E1. Okay, it is not E2 because E2 is not under capacity. And from V1, where do you want to go? V4 and then to T, right? Yeah. So let's go to V4 and then let's go to T. So observe that. So this is first of all not a die path. This is a path in the underlying undirected graph. Okay. So from now on, when I say path, I'm referring to the underlying undirected graph. Okay. And the undirected graph here, notice that it is not a simple graph. You have these parallel edges. E1 and E2, for example, become parallel edges in the undirected graph. Okay. However, for all the forward arcs, which means the arcs that are directed from S towards T in this direction of traversal. So this is our direction of traversal from S to T. In this particular direction of traversal, all the forward arcs are under capacity. However, this reverse arc, it is actually not under capacity. Observe that it is actually at full capacity. It is the arc E1 whose capacity is 1 and the flow x value is also equal to 1. However, on this reverse arc, we can actually reduce something. And if we increase on the V3, V2 arc, we will still have the conservation constraint to be meeting at this particular vertex. Okay. So what we want is that all the forward arcs are under capacity, which basically means that the x value is strictly less than the capacity, and all the reverse arcs, there is only one reverse arc in this situation, it has flow greater than 0. It has, maybe I won't say flow, it is confusing. Let me just say the xe should be greater than 0. Okay, if these two conditions hold, then I can actually again improve the flow. I can find a better flow by doing some modifications. Are there any questions or concerns regarding the discussion so far? Okay, so we are going to do that, and I'm going to write another flow here, and I'm going to once again be lazy and just use a green color to modify the current flow. All right, so on the arc S to V3, we want to increase. So how much can we increase or decrease by? Let us see. Um, the forward arcs, observe that the maximum you can change is by 1. Actually, give me a second. No, you can change by 2 actually, because they are all under capacity by 2. So either you have 2 and 4, 2 is the x value and 4 is the capacity, or you have 1 and 3. And in both these cases, you can increase by 2. However, the reverse arc that we have, which is the arc E1, we can only decrease by 1 because we need non-negative numbers. Okay, so let me first change that number. So this one here will become a 0. I can't decrease it anymore, right? Because I want non-negativity to be holding. And I will increase all of the others which are forward arcs by 1. So this 2 will become a 3. This 1 will become a 2. Um, this one here will become a 2. And this 2 here will become a 3. Okay. So what we have done, um, we have added 1 over here. We have added 1 here. We have subtracted 1 here. We have added 1 here. And we have added 1 here. Let us check the conservation constraints. At this vertex, the incoming has increased by 1 and the outgoing has increased by 1. At this vertex, the incoming has decreased by 1, which is the arc E1, and the outgoing has increased by 1. Um, Sorry, my bad. My bad. It's not a good idea to look at this drawing because um, sorry. What I meant to say is the incoming has increased by 1 and decreased by 1. So the total change is 0 and the outgoing change is also 0. Okay. Notice that both the arcs V3, V2 and E1 are incoming at V2. And we have increased one by 1 and decreased the other by 1. Okay. So there is no change. The same thing holds here. Here the outgoing and have increased by 1 and decreased by 1. So there is no change. And there is no change in the incoming arcs. And here it holds because it is the standard situation. You increase the incoming by 1 and you increase the outgoing by 1. Okay. Yeah. All right. So the conservation constraints still hold and the capacity constraints also hold. All right. So it turns out that this is actually the correct idea. So rather than insisting that we have a die path where the first condition holds, all of the x values are less than the capacity, turns out that the better idea is to also consider reverse arcs. So rather than looking at die paths, we'll look at paths and we will try to have these two conditions satisfied. Okay, so this is called an incrementing path, an x incrementing path. Okay, so these two conditions, condition 1 and condition 2, is the definition of an x incrementing path. And if an x incrementing path starts at vertex S and ends at vertex T, we will call it an x incrementing ST path. Okay. If Q starts at S and ends at T, the starting and ending is important because we need a direction of traversal, right? So that is why we need to specify where it is starting and where it is ending. Then Q is an x incrementing ST path. Okay. And the point is, whenever you can find an X incrementing ST path, you can improve your flow. You can find a better flow by doing the trick that we just did. All right. Are there any questions or concerns at this point? So let me just state the proposition. We have a max flow instance. And let's say we are given an ST flow. So the claim is that if there exists an X incrementing ST path, say Q, then we can obtain a better flow than X prime, which is defined as follows. So what we are going to do is, for all the arcs, there are three possibilities. So the arcs that are not in the path Q, right? So I'm viewing the path as a set of arcs rather than a set of vertices and arcs, okay? So whenever the arc is not in the path, I will keep it as it is. If it is a forward arc in the path, so E is a forward arc of the path Q, then I'm going to increase it by a certain beta value. We need to compute beta. We need to figure out what beta is. And if it is a reverse arc, then I'm going to decrease it by the same quantity in order to maintain the conservation constraints. Okay. And the claim is that this new X prime, where I need to still tell you what beta is a max flow. Yeah, is a flow which is better than the previous flow. Sorry, it's not necessarily a max flow. X prime is another flow, and the value of X prime is strictly greater than the value of X. Okay. In particular, if there is an incrementing path, then the given flow is not a maximum flow. X is not a maximum flow. Okay. And how do we compute beta? So we want to make sure that the forward arcs remain under capacity, and we want to make sure that the reverse arcs, they continue having a non-negative flow. So we're going to compute two betas, and then we're going to take the minimum of those two. Right? So the beta 1 is going to be, for all forward arcs, E is a forward arc of Q. We are going to take the difference between the capacity and the current flow value. Okay, current X value on this arc. And beta 2 is going to be, for all the reverse arcs, just take the minimum of the X value, because you can't choose a beta bigger than that. Otherwise, that arc will become a negative X value arc. Okay, so if E is a reverse arc, then you choose this, right? And beta is the minimum of beta 1 and beta 2, right? So this is the best you can do in order to still have flow, which will therefore necessarily satisfy the capacity and conservation constraints. Okay, so that is nice. Turns out this is actually if and only if. In fact, whenever you have a flow that is, whenever you don't have an X incrementing ST path, it necessarily means that the flow you have is a maximum flow. Okay, so in fact, the converse is also true. In particular, if there does not exist an x incrementing ST path, then x is actually a maximum flow. Okay. And that is the key idea behind the algorithm. So this should remind you very much of augmenting paths, right? In fact, I remember when we were talking about augmenting paths, yeah, I think it was Varun who raised the question that it looks very similar to what happens in flows. And that is not a coincidence. It is actually the same kind of concept. And in fact, if you try to solve bipartite matchings using flows, essentially your augmenting paths turn out to be the incrementing ST paths. Okay. I'm not using augmenting because we have already used it for matching, so I'm sticking to incrementing paths. Okay. All right. So let us assume that the converse is true, right? Let us say for now that we know the converse is true. Then this already gives us an algorithm to find a maximum flow. Every time you check whether there is such a path, and if there is, then you find a better x value, better flow. And if there isn't such a path, then you say that, okay, that's done. This is the maximum flow, right? The problem is, how do we find an incrementing ST path? Okay, so that is something we need to discuss. So um, assuming we know how to find an x incrementing ST path, we have an algorithm. Okay, so this is the only thing we need to now address: how to find such a path. And the other thing we need to address is, how do we prove the converse? Okay, so let's discuss these two matters. First, we will actually prove the converse, and then we'll discuss how to find an x incrementing ST path. Are there any questions or concerns before we move on to a fresh page? Okay, no? So let's go. All right. So, theorem 3.6. So let's say we have a right. So we have the same setting, HSTC, max flow instance, and we have ST flow, right? And we want to prove the following: if there does not exist an x incrementing ST path, then, so I'm going to keep some gap here. The main claim I want to make is that F is a maximum flow. Okay, so this is the main thing we are trying to prove. We will also be more specific and fill up this missing space. So how do we do this? Let us suppose we don't have an x incrementing ST path, right? If there's such a path does not exist, then how should we go about proving that this is a maximum flow? Assume there is no, sorry. X incrementing ST path. Any ideas on how we would be able to show that a certain flow, sorry, not F, I meant to say X over here, my bad. X is a maximum flow. So any ideas on how we can show that a given flow is a maximum flow? What are the techniques we know at this point to show that a particular flow is actually a maximum flow? Okay. Right. So I'll take the main part from that. So what Shantini is suggesting is that maybe we can find a certain cut, right? So what the only thing we know right now is that the value of any flow is less than equal to the capacity of any cut. That is the only way we know how to get an upper bound on the value of a flow. So in particular, if we can show that there is a cut over here, an ST die cut, whose value is exactly equal to, whose capacity is exactly equal to um, the flow that we have, its value, right? Then it would imply that this is a maximum flow. Okay, so that is actually the plan. The plan is to find or define um, an ST die cut partial plus of u such that the value of this flow is exactly equal to the capacity of this cut, right? If we can find or define such a die cut using some idea, then for sure we know that we can't get a better flow than the capacity of this cut, and therefore this is the maximum flow. Okay. Okay, great. So how do we do this? Let's draw a figure to get some clarity. So we are trying to define some set U of vertices that will contain S but not contain T. And we want to make sure that this cut, so we are looking at the edges going out here. We want to make sure that partial plus U, it has the same capacity as the value of this flow, right? This is the desired condition. Okay. So that is exactly what we want to do. How do we go about this? We want to find this kind of a die cut. So what should we do now? Right. Exactly. Yeah. So what we know is that there is no X incrementing ST path. Um, so let's look at what are all the vertices we can reach from S using X incrementing paths. So they will start at S, but they won't end at T because of course there is no such path, right? So we'll try to go as far as we can using these incrementing paths. And when we can't go any further, that will be the definition of our set U. Okay. So, sorry. No, because we could have everything reachable, right? The original graph is connected, right? Right. You're probably thinking about the auxiliary digraph, but we haven't constructed that yet. Yeah, yeah, yeah. So there is another way to think about it, but I'm going in a more, I'm going directly from this incrementing path notion. Okay. So what we will do is let U be the set of all vertices that are reachable from S using X incrementing paths. right? So which means we are looking at a path that starts at S, and this is the path in the undirected graph. So you could have reverse arcs. All these forward arcs should be under capacity, and the reverse arc should have x greater than 0, right? And these should have xe less than equal to ce for all of these forward arcs. Okay, so that is the definition of x incrementing path, right, that we saw earlier. So we're going to look at all the vertices we can reach. So we are not saying how we are going to find this, right? I mean, that's not the point. We are just trying to get a proof, right? So there is a set of vertices that will be reachable. Let us look at all these vertices and let us call that the set U. Okay, great. And I claim that this is the desired cut. Okay, so I claim that U has the following properties. The first property is that T is not in U, which implies that partial plus of U is an ST die cut. Okay, this is clear because the vertex, there is no x incrementing ST path. Therefore, T cannot be reached from S using x incrementing paths, right? So this part is clear. This just follows from the hypothesis. I claim that all the forward arcs in this cut, so each arc in partial plus of U is at full capacity. What I mean is the XE is equal to CE. And I claim that each arc in the opposite direction, so I'm looking at arcs in partial minus of U, I claim that they are at 0 x value. What I mean is that xe equal to 0. Okay. Can anyone in the call tell me why property 2 is true? So why is it true that if I look at an arc E going from little u in capital U to little v in U bar, why is it true that this arc is at full capacity? What would the contradiction be otherwise?
You could extend you could add
Exactly.
one more vertex.
Exactly. The vertex V should then be in U because you reach U and then you take this arc, and by definition of x incrementing path, you will have a bigger x incrementing path which will go all the way to vertex V. That is a contradiction, right? Thank you. So these two are easy properties, and I will just say do it yourself, and we just discussed one of them. Okay. But now what do we know? If these two properties hold, what can we say? Let us go back to our yeah. Right? We wrote a strengthening of the corollary. Sorry, not visible. It's the same page. Is it visible now? Okay, maybe a network issue. Yeah. So let us observe this corollary that we stated, right? Whenever these two conditions hold for the forward arcs and the reverse arcs in this cut, right? We know that the flow value is exactly equal to the capacity of the cut. But that is exactly what we want to prove, right? So let's go back. So by strengthening of, maybe I'll just say corollary 3.4. So these two conditions imply that by corollary 3.4, the value of the flow is exactly equal to the capacity of the cut. And that is exactly what we wanted to prove, right? So therefore, this is indeed a max flow and this is a min cut. Okay, good. So let's see, how much more time do we have? We have another 5 minutes. I don't know if we have enough time. All right, so this proves the max flow. Right, so this proves this theorem that if there is no x incrementing ST path, then x is indeed a maximum flow. Okay. And now how do we get an algorithm? And the algorithm will also prove the max flow min cut theorem. Okay, so let's say we are given HSTC as usual. So what we will do is we'll start with any flow, which could be just the zero vector. X is any flow, possibly the zero vector. Okay. And we have the following loop. So if there is an x incrementing ST path, Q, then we simply get a better flow using this proposition. Okay. So if there exists an x incrementing path, then let x prime is obtained from x by proposition which does not have a number star. Okay. Otherwise, there is no x incrementing ST path, and in this case we define the set U is set of all vertices reachable from S using x incrementing paths. And in this case, we will return the current flow and we can just return the set U, right? From U, we can get the die cut partial plus of U. Okay. This is not a complete algorithm in the sense that how do we find this x incrementing ST path? This is something we still need to discuss. And how do we find this set U? Okay. So this we will discuss next time. How do we find these? But let us assume that we know how to find these. Okay. In that case, how many times will we be doing incrementations? Observe that if the original capacities are integers, then the beta you compute will always be an integer. And each time you will increase the value of the flow by at least 1. Therefore, in a finite number of steps, your algorithm will terminate. Okay. So this is in fact the Ford-Fulkerson algorithm. So the point I want to make is that if the capacities are integral, then the algorithm, the Ford-Fulkerson algorithm, terminates in finite time. In fact, the maximum number of incrementations, in fact, the number of incrementations will be upper bounded by the maximum flow value, whatever it is, right? So if the maximum flow is 100, then you will have at most 100 incrementations, where f is the value of max flow. Okay, so this is for integral capacities. By using a trick that we did similar for matchings, you can also prove the same for rational capacities. So even for rational capacities, the algorithm will terminate in a finite amount of time. The only problem is irrational numbers, and in that case, you can actually not prove that this algorithm terminates in a finite amount of time. There are actually situations given by Ford-Fulkerson where the algorithm doesn't terminate because the capacities are irrational. But of course, for real-world applications, you generally don't have irrational capacities. So in fact, for rational capacities, the algorithm always terminates with a correct answer. And in fact, this proves the max flow min cut theorem, right? Because either this algorithm will find a maximum flow, otherwise it will find your minimum capacity of minimum cut, right? In fact, whenever it terminates, it will find you both. So the max flow is indeed equal to the min cut, right? So the correctness of the algorithm, the fact that it terminates, proves the max flow min cut theorem. This implies the max flow min cut theorem. Okay, good. What else? Yeah, so I think the only thing we need to discuss now is how do we find an x incrementing ST path, and how do we find this set of all reachable vertices. Turns out these are both using the same technique, and this we will discuss on Monday, but you can think about it yourself, and I'll give you a hint. So try it yourself, and the hint is construct a different directed graph so that your your x incrementing ST paths will become ST dipaths in this graph, in this directed graph. So construct another directed graph. Okay, try it on the example you have and see if you can yourself define this digraph, and then on this digraph you just have to check whether there's a directed path from S to T, which you can do using simple breadth first search. Okay, so that's all for today. Any questions or concerns? If not, I'll stop recording.